electromagnetic charges. And again, just to review, the law of charges means that like charges repel while unlike charges attract. And today we're going to experiment with that, or prove that somewhat. And I have made for this experiment a few devices here. A contraption with a hanging pith ball. These are everyday materials that you can find around your home or place of dwelling. And this is a number 12 wire. This is just a metal nut. Same here, just a heavy device for a base, so it could be a stable base. And here I have earplugs, used earplugs I cut up and hung by a string to the device, to the hanging devices here. And we're going to see if we can charge these pith balls and statically charge these pith balls, and to see how they behave in relation with each other. Again, we're going to perform these experiments with more or less everyday materials that you can do on your own, perform at your leisure with materials available around the house again. And to begin, we have to basically charge, to begin, one of the pith balls with a static charge, whether it be positive, negative, doesn't matter. We don't really know. And we're going to see how it behaves against an object and against another pith ball, which we have here. So we're going to use this item to charge it, a styrofoam plate that I think holds a pretty good amount of electrostatic charge, to see if we can transfer it. The theory is that if we touch the item with a charged object, it gains the same charge as the charged object. If we just approach it by induction, it gains the opposite charge of the object. So whatever charge this gets, positive or negative, I believe is a negative charge. If we rub it against a, for example, piece of fur or cloth, touch it, it'll get the same charge, negative. If we approach it, it'll get the opposite charge, or positive. So we'll rub it, charge it with negative electrons from this sweater to the styrofoam plate. And we're going to surround it from an area that they were of unlike charges. So even though this didn't demonstrate it, decisively, when unlike charges attract and like charges repel. We proved it in some instances, not so much in others, but we know that to be the case. This did not prove or disprove that. Next experiment I'm going to do is a electroscope, which I have built from basic materials. We have a mayonnaise jar, plastic clear mayonnaise jar, and we have again a number 12 conductor or wire coiled up top, and we basically put it through this nut device to hold it in place. That is an MC4 connector for solar cables, solar energy cables, which nicely put that through there. I made a hole in this lid or cap and secured it and tightened it quite neatly here using this MC4 connector. If you want to see it up close. And you could make this for any kind of school project or presentation or demonstration or experimentation at a place of learning or home, for a fun little demonstration of static electricity and electric charges, the law of charges. And that inside is just 2 pieces of aluminum foil cut in a teardrop shape, and you basically punch a hole through the middle and hang them by a hook on that wire. So the way that works is the following. Electrostatic charge is transferred either by conduction or induction. Conduction meaning touching it, induction meaning just approaching it. You put a electrostatic charge here, and it is transferred through the wire. So it is actually a charge, not electrostatic. It is electrical but not static, because it moves through the wire and it's transferred into the foil leaves. And since the same charge is transferred to the foil leaves, they both gain the same type of charge, whether positive or negative, and they repel each other. That'll demonstrate that like charges repel decisively. You can see that clearly here doing the demonstration. Again, we're going to rub this styrofoam plate that seems to hold a lot of electrostatic charge quite well. We're going to rub it in this piece of cloth, build up some static. It's electrostatically charged. We do it by induction or nearing it up top, not touching it, and we'll see if the leaves, the foils, actually repel each other. Didn't quite work there, but I'm going to rub the styrofoam cup on my hair. Doesn't seem to work quite well. It must be a very humid morning. The drier the day, the better this works. Okay, now we can kind of see it. When I approach or near the plate, statically charged plate, the aluminum leaves appear to separate from each other. You can kind of see them nearing the plate, separate, pulling the plate back, they come back together. Nearing the plate, they separate a little bit, pull the plate back, come back together. Near the plate is near, the foil leaves separate a little bit. It's a quite humid morning, so the static is not transferred as much. I've seen it split up quite dramatically. Not today, only very slightly. I'll try it here to see if I can get a better shot. I'm rubbing the styrofoam plate, charging it statically, electrostatically, and I'm nearing the plate now. You can see it move and turn, and there we got a very good split. The plate is near the coil up top. I want to remove it. 1, 2, 3. Closes up. I'm going to approach it. 1, 2, 3. Opens up. Got a pretty good charge here. I rubbed it in my sweater. It seemed to work a lot better. So we have light charges transferring through the wire and into the foil leaves equally, so they repel each other. So I'm going to pull back the plate. They come back together. And that is the electroscope. The electroscope experiment using just everyday materials. Approach the plate, and you can see a very pronounced split on the aluminum foil leaves, and they remain so as long as that plate is near that coil. So what happens if I touch it? If I touch it, it transfers even more. So the split is even more pronounced. I touched it, I backed up, backed it away, and touch it again, same thing occurs. That is the electroscope experiment. The next experiment I'm going to be performing. And by the way, I've done this with a balloon, where you charge the balloon, approach it. And it seems to work with the balloon even without rubbing it right now. As you can see, I'm approaching the balloon to the coil, and they're splitting up. I just rubbed it with my sweater again, and it's still splitting up. Okay, the next experiment. It's with a homemade battery made with everyday materials. This is a weak battery at that, but it shows the concept of a battery, which is a voltaic pile, voltaic cell. And all I'm doing here, all I did was to basically attach a penny to a wire. This is a penny. And in this case, a nickel. Attach the nickel to a wire. And from that, we can make a simple battery. See, battery is nothing but two different materials, usually materials that can hold and transfer charge. They're usually metals. That's what a battery is made of. Not necessarily these materials, but others that perform the same task that I'm about to show you. So we have a meter. For that, we need a meter to measure the voltage that the battery generates. Need a couple of leads to make it a little easier. We attach the negative lead of the meter. Again, we have two battery terminals. We have one pole and another pole, and one of them is a positive, one of them is a negative. Anode is positive, cathode is negative. Okay, so we'll call these our negative to see if it's the more negative of the two. I'm not sure whether it's the penny or the nickel that is the more negative of the two, but we'll see. And we'll attach the positive to the wire from the nickel into the positive lead of the meter. This is a voltmeter. And this meter is a analog, older style meter. You can see in the background. And it's set to milliamp for voltage, for DC voltage. I have it at the, I'm going to put it at the lowest setting because it's going to be a very low voltage. 0.25 or a quarter of a milliamp. 0.25 milliamp DC. DC milliamp. And the one I'm going to be reading, if I got milliamp, DC milliamp, I'm going to be reading DC milliamp, this gauge right there. I'm going to be reading from that second from the top gauge. Okay? From 0 to 250 milliamps. From 0 to 250 milliamps. Second from the top. Second from the top. It's nicely labeled, so there's no confusion. Okay, this is two parts, anode, cathode of my battery. Something else is missing though. My medium for electron transfer. To go ahead and transfer electron from one pole to the other, one from the anode to the cathode. If we touch them together like the experiment says, there's no voltage detected. As you can see, I have them connected. However, there is no voltage reading. I have them touching. However, there's no voltage reading, as you can see. Put the light on so you can see a bit better. There's no voltage reading, or if there is any voltage, it's undetectable by this meter. But let's see what happens when we put a transfer medium, like some type of moist liquid or moist paper, like this piece of tissue. It's not moist, it's dry, so let's see what that does. Nothing, it's dry. It doesn't transfer anything, doesn't allow any transfer of electrons. Now I'm going to lick it, put a little saliva on it, aka water, mostly water, and a few chemicals. We'll see what that does. I'm going to put one in between each other, a pile, and we can see the needle moving already. This is a voltaic pile. You need a transferring medium, which in batteries is mostly dried chemicals, sometimes liquid chemicals like battery acid. In this case, we have a chemical like saliva or spit. And we already see a very small voltage detected. You can see the needle moving. That needle moving means there's a transfer of electrons. I'm going to wet this a little more to see, help it out. So it's picking up voltage, as you can see. And that, my friends, is a simple battery. There is a continuing transfer of electrons between these two metals. That is the definition of a battery. Let it go, goes right back to near zero. Put them together, it detects a few milliamps of a DC voltage. Now let's see if we can get a more dramatic effect out of these two metals with a little richer, a somewhat richer medium, a little bit of a richer medium. And for that we choose a potato and we insert the nickel as such. Remember, the nickel is tied up to the positive lead on one end. On the other end we insert the penny. I have already cut some slits on this. I believe this to be one of them. So we insert the other end of the battery, the cathode, and the potato battery as such. So let's see if we have a reading. We have quite a bit of reading already. We have more than a few milliamps. About 5 milliamps, 6 milliamps. So it's the transfer of electrons is more pronounced with the potato. Take it off, close to nearly zero, put it back on. You can see the voltage. Again, this is not voltage coming from any kind of source other than these two dissimilar metals and the chemicals in the potato, and it's detecting a voltage right here. That voltage is probably enough to power a small radio. Those are DC milliamps. Another experiment I want to perform is by an experiment that shows the battery connections of parallel and series, the series and parallel connection of batteries, which are sources of power. Remember, in your circuit you have your power source, which could be a battery. Among other things, you have a conductor, and you have a load or some kind of resistance. Sometimes you can also include a switch in a circuit. In this case, we're just going to have conductors and a power source, and we're going to connect these in series just to show how batteries are connected in series. As an experiment with our meter, we're going to see what difference that makes as far as your voltage, which is your EMF, electromotive force, or your potential difference. We'll see what the series type of connection does to your two things, your voltage and your current. Your voltage is basically your pressure, electrical pressure, that can push electrons out, and your current, or amperage sometimes called, is basically the flow of electrons, which depending on the connection type that you have, either series or parallel, you can extend or it could remain the same. We'll see by doing an experiment, this experiment, how the different connections affect those two, voltage and current. So we have two batteries, 1.5 volt each, and you can see the voltage of the battery right on the battery. Many times it's written on it. In this case, is right on the battery right here. A little better light if you can see that. 1.5 volt. This size battery, and that is your voltage, your pressure, your electrical pressure. Sometimes it also tells you your available amps, which is measured many times in milliamps in batteries, or milliamp hours, which is the amount of time that you can draw a certain amount of amperage from the battery. In this case, this one doesn't appear to have that information, but we don't really need that at this moment for this experiment. First, we want to connect the batteries in series, and when you connect something in series, you can review this in the available text for this course. When you connect something in series, your power, for one, remains the same throughout the circuit. We'll see if that holds true in this experiment. That's one. Second, your current is additive throughout the circuit. At each resistance point, your current is the same. This is again on a series circuit. And your resistance is again also like voltage, additive. You add it at each point of the circuit. You have different resistances. You add those up, you get your total resistance. For voltage, the same thing. You have different voltage drops at each location. You add those up, you get your total voltage. Again, in a series circuit. So connecting these in series is easy. You just connect them as such, with your positive pole of the battery, shown here, touching your negative pole. So negative to positive, and you have available a positive pole and a negative pole to test. So what you do basically is get your meter leads. You put your meter at the voltage that you expect. This is what this dial is for. So the voltage that we expect right now, what is it? If we have 1.5 volt and 1.5 volt in a series circuit, they add up. So in a series circuit, the voltages add up. They're additive. So we have 1.5, 1.5. Add those up, we have 3 volts. So we expect to read about 3 volts, sometimes a little less, sometimes a little more, depending on the state of your battery. So here we have the selector at DC volts, 10 volts. The next lower one is 2.5. 2.5 is a little low. It'll top off the reading on the scale. So the next one up is 10. We select 10, which is going to be this meter scale here. Second one from the top. See that 10? That's 10 volts, volt DC. And we should read in increments of, looks like 2. So again, put your meter leads, negative, positive, see what we get. Negative, positive. We have it in series. The meter may be off, so let me cycle it. Make sure the leads are on. So connected in series, the batteries, we should get a reading. In this case we do. And if you can see that it's close to the 4 on the scale that we pointed at. So we have about 3.5 volts. It's a little over the 3 mark. So our voltages have doubled. The voltage of one battery has doubled since we have 2 batteries connected in series. Again, positive to negative. And you should always have 2 poles available for reading. When you connect in series, never connect, when you have wires involved, never connect these 2 poles together. Like if you have this wire, for example, you never want to connect these 2 poles together, because this wire is not a load, it's not a resistance. It has very little resistance and it'll just heat up the wire until it burns. In some cases, in this case, since we're talking about small voltages, it'll just drain the batteries and it will heat up the wire, and the batteries probably will get damaged because of the high currents involved gained, because this is basically offering no resistance, so the current is going to max out. And we can work that out using Ohm's law. If you want to work that out, that's probably an interesting thing to find out. What will the current be if you have a resistance of, let's say, 0, practically in this case, for a set of batteries connected in series. So we can just work that out mentally or verbally here real quick. I mean, if we have the Ohm's law formula of voltage equals to current times resistance. Resistance is 0, right? So your current is unknown. That's unknown value. Your voltage, you know your voltage is 3 volts. So let's remake or reorganize the Ohm's law, which we can do it as I, or current, equals to voltage divided resistance. So voltage divided resistance in this case is 3 times 0. Let's see what we get when we say that. So 3 volts times 0, we expect to get 0. But we're not multiplying, we are dividing. So I'm sorry, we get 3 volts divided 0. We get an error because we get basically the whole voltage instantaneously. We get an instantaneous current rush with the entire voltage behind it. In this case, 3 volts. So we'll move on to our next type of connection, which is our parallel connection. Again, using parallel, the known rules and laws of parallel circuits. We know that our voltage will remain the same throughout the circuit. We know that our current is additive, meaning that if we have 2 batteries and they have a certain amount of current in each battery, those will add, or in this case, current available, or amp hours, milliamp hours in this case. But we're going to keep a voltage of 1.5 volts, which is the same. In this case, we can go ahead and connect pole to pole as long as it's positive to positive, because all that's doing is extending or doubling the size of the battery as far as current. But remember, we are keeping the same voltage. So we put this wire with tape as such, and we're basically, what we have here basically is a a parallel connection. We call it parallel because notice how those wires they are in parallel with each other. That's where the name parallel comes from. We connect them as such. So basically, we take these two batteries and make them into one. That's effectively what we're doing. So our prediction is that we're going to remain with the same amount of voltage according to the laws, Kirchhoff's law, and we are going to double our current. We're just going to test for voltage in this experiment. Maybe later we'll test for current, see how current changes. But in this experiment we're looking at voltage. So remember, positive ends on this side, negative ends on this side. So we want to read a positive side and a negative side. We're going to flip our batteries. Hopefully our wires won't come loose. And that way we have a positive and negative pole available for reading. And we're going to switch it up since we have a positive on this side, negative on the other. We're going to bring it back to 2.5 on the dial, since we expect to read less than 2 volts. We expect to read 1.5 volts because each battery is 1.5 volts. That won't change. And 1.5 volts, we use which scale? If you can see the meter, which scale are you thinking that this setting will use? I would think it would use, not this one. I would think it would use this same scale, second from the top. Since it has 250 up top, that could be transformed or equivalent to 2.5 DC volts, or volts DC. So we'll see what kind of voltage that gives us. We connect the negative side, positive side, and we get a reading of nearly 1.5, 150 in the dial, in the needle scale, but that is translated to 1.5 volts. We can also use, this one has a setting of 1.5, and it'll be close to topping off 1.5 volts. That's typically for battery testing. So we'll see what that does. That's probably going to top off our reading. Connect your poles.